Hi there and welcome to this video for Senior Physics on Motion. In this video we're going to explore the equations of motion. Basically there are four main equations that we use in physics to basically describe and determine what things are happening in a journey when something is moving. All of these equations come from our graphs and you'll see how they incorporate together. Now, although we're going to run through how the equations come about, this has got nothing to do with assessment. You won't be assessed on how they come about, but it's interesting to know and see the science process that through observation and graphical representation, the algorithms can be generated, and these algorithms are the ones that we utilize in our everyday classes in physics. Okay, so let's get started and see where we go. All right, now we know that for constant velocity, the equation that we've got is velocity equals distance over time. As you can see, v equals s over t. This comes from the gradient of a displacement time graph. Now, as we know, if the velocity is not constant, then we can work out the average velocity by looking at the overall distance covered in the time taken. Now, distance and velocity, as we say, can be rearranged so that we get s equals v times t, which will then give us the distance. So by manipulating the formulae, we can actually start substituting them into other algorithms, and this is how we get a variety of different algorithms that we can utilize. Now, if we're looking at uniform acceleration, we use a variety of different symbols. A will generate our acceleration, u will be our initial velocity, v is the final velocity, s is the distance traveled, and t is the time taken. Now, depending where you are around the world, the initial and final velocities may change with respect to the symbols. As I've mentioned earlier, initial velocity can often be written as v subscript little I, and final velocity is v subscript little f. Sometimes distance is given the symbol d, but generally s is the general form that we will use. Okay, so let's get started and start manipulating the formulae. Now, we know right from the beginning that distance traveled can be determined from a velocity time graph and looking at the area under the graph. Now, in this velocity time graph, you can see we've got v and u, and we've got t, and we've got to determine the area under the graph. Well, the area under the graph is denoted by the algorithm s equals u plus v divided by 2 times t. Now, this basically comes from the trapezium rule, where the two sides are added together and then divided by 2 and then multiplied by the base. So from this we get the distance will equal the initial velocity plus the final velocity divided by 2 times t. This is equation 1. So for equation 2 we can determine the acceleration. Now we know that acceleration equals the change in velocity per second. Now we know that a equals v minus u over t, noting that v minus u is the change in velocity divided by t, which is the time. Now, rearranging this, we can now generate a equation where we make v the subject. Now, making v the subject will make relevance for equation 3. So if we rearrange this, we get v equals u plus at. v equals u plus at is now equation 2. Alright, so for equation 3, what we can do is we can combine these two equations. We can substitute equation 2 into equation 1 by substituting in for v. So, what we then get is v going in from equation 2 into equation 1, and it gives us this overall algorithm that the speed equals u plus at divided by 2 times t. Now, when we simplify that, we get 2ut plus at squared divided by 2. Now remember, the two 2's can cancel out for 2ut, and that leaves us a half plus a half at squared. So our third equation is s equals ut plus a half at squared. So to recap, we've got the trapezium rule, which is equation 1. We've got an arrangement of the acceleration algorithm. Remember, acceleration came from the gradient of a velocity time graph. We've substituted those two equations in together to get a third equation. Now, this third equation now gives us a value for a. We have a incorporated into our equation. So we've got four variables which we are looking at: s, u, T and A. Okay, so now what we can do is rearrange equation 1 to make T the subject. So let's take equation 1 and rearrange it. Actually, this is equation 2, apologies there. So V equals U plus AT, and we rearrange it to make T. Now we substitute this equation and we basically get V squared equals U squared plus 2AS. Okay, so we've rearranged them and substituted them in, and this is where our fourth equation comes from. Alright, so that gives us a sort of breakdown as to how the equations come about. Note, there's nothing complicated there. It just comes from observations, which were then graphed. The gradients of the graph gave us the algorithms, and then all we've done is rearrange them and substituted the values in to get our four equations. Now, our four equations we can see here: V equals U plus AT, V squared equals U squared plus 2AS, S equals UT plus a half AT squared, and S equals a half V plus U times T. So hopefully you understand where they come from, and again it runs through that scientific process. So the question now is, how do we use them? Well, when we get a problem, the first thing I always get my students to do is to write down what you know from the question. So write down, you will be given 3 variables that you know, and you'll be expected to find a fourth. So write down what you know first. The second thing is to write down the symbol of the quantity that is required. So you'll have 3 knowns and 1 unknown. From that, you then select one of the equations from the equations in the blue box. Remember that you're going to have 3 knowns, 1 unknown, and you choose the best equation which will best suit your problem. So let's look at an example and see how we can put this together. So in this example, we've got a stone which is released from a height of 20 meters above the ground. Neglecting air resistance and using the acceleration due to gravity as 9.81 meters per second, we've got to find the velocity with which the stone will hit the ground. So following what we've done, let's do 1 and 2. In 1 and 2, we know that U equals 0 because it states it goes from rest. The distance is 20 meters. Acceleration is 9.81 meters per second, and we've got to find V. So I've got U, S, A, and V. So going to my blue box at the top, I choose the correct equation that has U, S, A, and V in it. And in this case, we end up with V squared equals U squared plus 2AS. I then substitute into the equation and solve, and I end up with 19.8 meters per second. So it's a very straightforward process. Always logically write down what you know, what you were trying to find, select the correct algorithm, and then process the data. If you follow this in each situation, you won't go wrong. So let's take another example. In this example, we've got a radio-controlled toy car which starts from rest and accelerates with a uniform acceleration of 0.5 meters per second in a straight line. And we want to work out what speed does it reach after accelerating for 4 seconds. So pause the video now and see if you can calculate it using the process that we showed on the previous slide. Then come back and we'll run through the answers. So pause now. Okay, welcome back. So how did you get on? Did you struggle, or did you manage to come up with an answer? Well, let's see how you did. So the first thing we want to do is to basically write down what we know. We know U because it starts from rest. We know A, we know T, and we're trying to find V. So it's basically using V equals U plus AT in this situation where we're going to be trying to find V. So we've now got our algorithm. Write down your algorithm, substitute in what you already know, and then basically we come out and process with our answer that V equals 2 meters per second. How did you get on? If you manage that, it doesn't get much more complicated than that. Obviously, if you're going to be doing more A-grade questions, then you may have to incorporate, find one variable and then have to incorporate another equation to actually try and get a solution. But if you follow this logically, you shouldn't have any problems. Okay, so check out the exemplary video. I've put another example together where we work through some problems, and then there's also a worksheet which is linked to this post. I hope you found this useful, and good luck with solving equations of motion problems. I look forward to joining you again. Thanks for watching.